This is a 2-meter long cantilever beam with a rectangular section 60 mm by 90 mm, and it is subjected to a UDL throughout its length with the intensity 4 kilonewton per meter. You have to determine what is the maximum bending stress 1 and its location. And the second point, what you need to determine is the nature of stress at a point P, which is at a distance of 1.5 meters from the free end. And 15 mm below neutral axis. Okay, this is the problem what is given. So what we have is, let us take that beam first. So this is our beam. Okay, and here, let us say this is our extent now. Okay, and it is carrying UDL for its entire length. This UDL is of 4 kilonewton per meter, and the length is 2 meters total length. This is the fixed end. Let us say this is A and this is B. Now, this cross section is told to us. The cross section is a rectangular section here. Okay, so this is the rectangular section, and the size of this cross section, what is given to us is 60 mm width. This is B into D normally. So this is 60 and this is 90. Okay, so 60 mm and 90 mm here. That is the cross section of the beam. So for the solution, what you have to find is, first one, the maximum bending stress. Okay, the first thing what is asked is determine the maximum bending stress and its location. This is maximum bending. Okay, for this, we'll be using the flexural formula, that is in this, we'll use the ratios which relate the stresses and the bending moment. Okay, that is M by I is equal to sigma by Y. So from this, I can obtain what is the bending stress sigma, which is M by I into Y over here. Okay, so for stress to be maximum, we need to locate a point where bending moment is maximum, first thing, and the location of the point within the cross section should be at the extreme most distance from the neutral axis. Okay, now if you go for identifying the neutral axis in this case, it will be exactly at the middle. We have the rectangular section, so this is the neutral axis what we have. So this neutral axis will be at the center of the depth over there. So that is our neutral axis. So rectangular section, neutral axis will be, in our case, the neutral axis coincides with the centroidal axis. That is what we have concluded here. So for a straight beam, neutral axis coincides with the centroidal axis. So first is I'll locate the neutral axis, which is the centroidal axis itself. So it will be at the center. That is at a distance of d by 2 from both the ends. So d by 2 over here and d by 2 over here. Depth by 2, half at the mid depth. That is the location of neutral axis. And same you'll find it along this length also. So this is our position of the neutral axis at the mid depth. That's the neutral axis, what we have. Okay, now once we know the neutral axis, now we'll go for determining the maximum bending stress. Okay, to measure my distance y, distance of extreme fiber, I require the position of neutral axis first. With respect to that neutral axis, we are finding the distance y over here. So this is all the neutral axis, or this is the axis of the beam. Here it is exactly at the mid depth, right? So for this stress to be maximum, so for sigma to be maximum, we require two things. One is we need to have m has to be, or m and y both have to be maximum here. I is constant for the given section. So what I have is m and y have to be maximum. So where do I get maximum bending moment in case of a cantilever beam? So if you just recall that bending moment diagram for the cantilever beam, so you'll get the maximum bending moment at this fixed end. Okay, WL square by 2. So this is what we have the bending moment for the cantilever beam. The beam was, this is a beam, okay, and at this fixed end we come across the maximum movement over here. Okay, so for a UDL, the variation will be something like this, parabolic. Okay, so this is the maximum bending moment. So at this end, at the fixed end, the bending moment will be WL square by 2. The maximum bending moment will be WL square by 2. So maximum bending moment in a cantilever beam, it will be at the fixed end. Okay, and also for a beam with UDL, the maximum bending moment, okay, will be equal to WL square by 2. And this is a hogging bending moment, so negative. Okay, just to indicate the nature of bending, it is taken to be negative. This is a hogging bending moment. Now what this comes out to be here in this case, so in our case the maximum bending moment value m will be, intensity of load is 4, span is 2 meter, so 2 square divided by 2, or m will be equal to 8 kilo Newton meter here. Okay, now what about the y value, the distance of extreme fiber from the neutral axis? So if you measure the distance of extreme fiber from the neutral axis, in this case, what is the distance of extreme fiber from the neutral axis? So we have the neutral axis exactly at the mid depth at this point. Okay, so what you have, the top and bottom fibers are the extreme fibers. They are at the extreme most distance over here. Okay, so this is 45, okay, and this is 45. So I'll be considering the points at the two edges, top edge or bottom edge. These are the points over here, okay, or at this point. These are the points where we'll get y maximum. Okay, also what we have, distance of extreme fiber y max will be equal to d by 2, or this is equal to 45 mm in our case. Okay, now another property what we require is moment of inertia, that is moment of inertia of a rectangular section. So we need I in that flexural formula. For this section, it will be BDQ by 12, which comes out to be B is 60 into 90 is the depth, cube upon 12 here. Okay. So what this value will be coming out, I value. So this will be 364.5 into 10 raised to 4 mm raised to 4 over here. Okay. So these are my values which I can use it for determining the maximum stress. So if I substitute these values in our bending the flexural formula, okay, the formula what we are considered, m by I is equal to f by y, or sigma by y, or in other words sigma can be expressed as m by I into y. Okay, so we have taken this y max here to obtain the maximum stresses. So bending moment was 8 kilonewton meter, or it will be 8 into 10 raised to 6. Okay, that is 8 kilonewton meter. If you convert it to Newton mm, it will be 8 into 10 raised to 6 Newton mm here. Okay, so that's why 8 into 10 raised to 6 divided by, this was 364.5. The I value what we got was 364.5 into 10 raised to 4. What is the value of extreme fiber distance? It is 45 mm, d by 2, 90 by 2, 45. So what we have, sigma max, maximum stress. How much it comes out? If you calculate this one, any answers for that? Is it 98.8? What you get? Please tell me.
98.8.
Okay, 98.8 Newton per mm square. Okay, they are also asked for telling what is the nature, okay, maximum bending stress and its location. Okay, and its location is, it is at the fixed end. So maximum stress is at the fixed end because the moment is maximum at the fixed end. The maximum stress occurs at the fixed end and at top and bottom edges. Okay, I can say this as plus or minus 98.8. Why is because if I consider a point on the top edge, it will be subjected to tension. Okay, so tension, that will be plus, we can take that to be positive. Whereas if I consider a point on the bottom edge, bottommost edge, these fibers will be under compression. Due to bending nature, these fibers will be subjected to compression. So what I can say, plus or minus 98.8. On the top, tension will be there. On the bottom, compression will be there. Okay, so that is the bending stress nature, how it varies. So even I can show that plot for that bending stress, variation in the bending stress. So this is something what you have. If you plot that bending stress along across the depth of the beam, across the depth of this cross section, if you plot this one, so you will be getting something like this, the variation. This is what the variation in bending stress will be. Okay, so this is what we have. So this is 98.8 positive, negative 98.8. These are the stresses what you find on one face, top of the neutral axis tension, bottom of the neutral axis compression. This occurs in case of hogging moment. Compression. Exactly at this point, at the neutral axis, stresses will be zero. Okay, at this point, the stresses will come out to be zero. So that's the variation of bending stress across the depth of the section. Okay, what you are seeing here is bending stress variation across the depth of the section over here, what we plotted. On top we are getting tension and on bottom we are getting compression when the beam is subjected to hogging moment. This is your cross section over here. So that is with respect to the cross section what is plotted. Is that fine? Determining the bending stress. So if you consider any other point within the cross section, you will be able to get the other values of bending stress also. Like for example, in this second part of the question, okay, what is asked here? It is asked to determine the bending stress at a distance of 1.5 meter from the free end. Okay, 1.5 meter from the free end and 15 below the neutral axis. So I'll be finding bending stress somewhere over here at this location. This is my point over here. Okay, that is the point P, what is given to us. This distance, it is at a distance of 1.5 meter from the free end. Okay, so that is the distance what you have. This is where you need to find the bending stress in second case. So this is at a distance of 1.5 meter and 15 below the neutral axis. Okay, so let us take for that and determine that. Now for that purpose, what you require first is you need to find what is the bending moment at a distance of 1.5 meter from the free end. Okay, 1.5 meter from the free end, and then we'll go for determining the bending stress at that point P. Okay, this is the point P, 15 below neutral axis. So the distance y is given to us now in this case. Y is 15 That is the distance where you need to find the bending stress. For that, first what I'll find is bending moment at a distance 1.5 meter from free end. Okay, so what will happen to the bending moment here? M will be equal to W L square by 2 only you can find out, but in this case L is not 2 meter, it is 1.5 meter, or W x square by 2 I can write instead of L. I can write W x square by 2. Anywhere within the span of the cantilever beam, the bending moment can be expressed as Wx square by 2. Now in this case, x is 1.5 meters here. Okay, so or this comes out as 4 into 1.5 square divided by 2. So how much will be that? 4 into 1.5 square by 2.
So it will be 4.5.
Okay, so this will be 4.5. So here m will be equal to 4.5 kilonewton meter. Okay, and what we have, and y is equal to what? Y is told to us it is 15 now at a distance of 1.5 meter. One thing is bending moment value is 4.5 kilonewton meter, and what you have to find is the bending stress at a distance of 15 below the neutral axis. This is the location of neutral axis. 15 mm below the neutral axis, how much is the bending stress? So we'll consider the same bending stress equation from the flexural formula. Sigma is equal to m by I into y here, or this comes out as 4.5 into 10 raised to 6 Newton mm divided by y, 364.5 into 10 raised to 4. Y here will be 15 mm. Okay, so this is 15 mm y. So what it comes, sigma at a distance of 1.5 meter and 15 mm below the neutral axis. 4.5 divided by 364.5. Please calculate that on your own. So how much it comes out? What I'm getting is 18.
18.52.
Is that correct? 18.52. Okay, 18.52 Newton per mm square. What should be the nature of the stress? Whether it will be plus or minus, whether it will be tension or compression. The point is below neutral axis. Okay, so in case of hogging movement, okay, all the fibers below the neutral axis are experiencing compression. In case of sagging movement, the fibers below the neutral axis will be in tension. Okay, I showed one of the bending nature, okay, in the beginning. So you need to remember from that whether the bending stress will be in tension or compression. So what we are dealing with now is such a type of bending, hogging. Okay, so here the fibers below the neutral axis are in compression. So whatever stress we have determined, this 18.52, this is compressive stress. Okay, compressive stress. So that is the nature of stress over here. Any difficulty in that part for determining the bending stress? In first case, we went for determining the maximum bending stress. For that, first we calculated the maximum bending moment and the maximum distance of the point from the neutral axis, y max. Okay, so for the cantilever beam, the bending moment will be maximum at the fixed support. Okay, and from the neutral axis, you have to measure the extreme distance of the fibers. So here we have the extreme distance as top and bottom edges over here. Okay, they are the points which are at farthest distance from the neutral axis in this beam. Okay, so the y max value will be d by 2. Okay, because neutral axis is at exactly at the mid depth. For that purpose, we'll get it as d by 2. So from that, we considered or we used these values in the flexural formula. Okay, and we obtained the stress, maximum bending stress. In second case, the point where the stresses have to be determined was given to us. Okay, the location of the point on the span as well as the with respect to the neutral axis, it was told to us. For that, we went for determining the bending stresses. Uh, let's take one more problem here. A beam has a T section. A beam has a T section as shown in the figure. The allowable stresses for the material the allowable stresses for the material are 90 MPa in tension and 120 MPa in compression. Determine the moment of resistance for the beam. Determine the moment of resistance for the beam when it is subjected to when it is subjected to sagging moment. First one, sagging moment. Two, hogging moment. Okay, so you need to determine the moment carrying capacity of the beam. Okay, so the question is all about determining the moment of resistance or the moment carrying capacity for a cross section which is given to us. See, this is the cross section. What is there? It is a T section here. Okay, so this is the flange of the section and this is the web over here. So this is our web of the cross section. So that is the cross section what we have. Sorry. Okay, so this is the web of the cross section. So that is our cross section. Now dimensions what are given here is the flange width is 150 mm and thickness of flange is 6 mm. So this flange width it is 150 mm. Thickness of this flange is 6 mm. Depth of the web is 180 mm and thickness of web is also 6 mm here. Okay, so these are the dimensions of this cross section. Now before we proceed with determining the moment of resistance, what we require is one of the property of this cross section, that is the centroidal axis has to be located, because that itself will be representing the neutral axis of the beam. So when we find the neutral axis, then we can determine what is the extreme fiber distance y value. Okay, so first is centroidal axis. Centroidal axis location. What I mainly require is what is this y bar value. I need to locate the centroidal axis over here. So let us say this is the centroidal axis and we need to locate its position with respect to the flange. We can take it with respect to the flange over here. So we have two areas, rectangular cross sections. So I can apply. Okay, so from the first principles, what we'll do is we'll obtain the location y bar. Okay, this is my y bar location of the centroidal axis. That itself is my neutral axis here. Okay, so y bar, we have two areas, a1 y1 bar plus a2 y2 bar divided by a1 plus e2. This is how you get the location of the centroidal axis y bar here. I'm taking movement of areas about this top flange. So what is my a1? I'll call this as a1, and this is my a2, second area, a2. Okay, so just keep calculating to get that y bar value. Okay, so y bar, this will be equal to a1 is 150 by 6 into 6 by 2. Y1 bar, centroid of this first area, from the top flange, it will be 6 by 2 plus y2, what is that? 6 mm width, 180 mm depth, 6 by 180 rectangle section, and y2 bar will be somewhere here at the mid depth 180 by 2. So 6 plus 180 by 2. This is our y2 bar. This whole thing divided by total area, that is 150 into 6 plus 6 into 180, a1 plus a2. So what is this y bar value? How much you get? Yes, what is the answer for that? Y bar will be equal to how much? Any answers for the y bar value? Uh, 53.72. Is that correct?
Yes, sir. Yes, sir.
53.72 mm over here. Okay, so that is the first step, what we determined, y bar. This also gives us the location of neutral axis. Centroidal axis itself will be the neutral axis for straight beams. Okay, now next what I require is what is the moment of inertia of this section about the centroidal axis. Okay, so I have two rectangles, so I need to find what is the moment of inertia of these two rectangles about the centroidal axis. Okay, so normally you got it as bdq by 12 here. Okay, but in this case the centroidal axis for the entire section is not coinciding with the CG of these individual areas. So we need to apply the parallel axis theorem. Okay, so this will be A into YC square. Okay, IgG plus A into YC square. So that is the parallel axis theorem. IgG will be the moment of inertia about their own centroidal axis. You need to break up this problem in step by step. Okay, you need some basic concepts to be applied here to obtain this or the moment of inertia. So first, if I take this parallel axis theorem, apply it to the first area, my A1 area. Okay, so what it gives me, what is the moment of inertia of the first area about its own centroidal axis, B 150. Okay, so let me write here IgG for a rectangular section. It is given by BDQ by 12. For me, both the sections A1, A2 are rectangular sections. So this is applicable for both. 150 into 6 cube divided by 12. Okay, plus its area is 150 into 6. What is this YC term? YC is distance of the CG of first area from our centroidal axis. This is YC over here. Okay, so it comes out to be how much? Now Y bar is 53.72. Okay, 53.72. In that I'll deduct 6 by 2 because this CG of A1 is exact at the mid depth 6 by 2. So this is the distance what I need as YC. So square of this. Okay. So this is the parallel axis theorem applied to the first area A1 plus when I take the second area. Okay. Again BDQ by 12. That is moment of inertia of the second area about its own centroidal axis. B is 6 in this case, 6 mm. Okay. The dimension which is parallel to our axis will be taken as B. Okay. So B into D is 180 here. 180 is the depth, 180 cube divided by 12, BD cube by 12 plus area is 6 by 180 A2 area into what is YC now. Okay. So YC I have to measure it from this neutral axis, right? So let us first express both the distances. Distance of the centroid of second area from the top flange, how much it comes out. So it will be 6 plus 180 by 2. Okay, 6 plus from here d by 2. That is 180 by 2. That is 96. This will be 96. Is that fine? You got that one? 96. In that 96, if I deduct this y bar, I'll be getting this distance, which is YC for the second area now. Okay, we may call it as YC1 and this is YC2. So what it comes out? 96 minus 53.72 square of this YC square. So this altogether will tell you what is the moment of inertia of that T section. What is the moment of inertia of the T section about its own centroidal axis? That is about this axis NA, about the neutral axis. So what will be this answer? That is 150 into 6 cube by 12 plus 150 into 6. If you get me, tell me the answer. We require two things. One is location of centroid first, then the moment of inertia of the section about that centroid. Is it 7164.57 into 10 raised to 3? Do you get this much value of I?
Yes, sir.
Fine, 716. Okay, or else you may get it in terms of 10 raised to 6 also. Done. Or 7.1645 into 10 raised to 6 it may be, if you get it in other factors. Okay, now we have the properties of the section here. Now next thing is to determine what is the moment of resistance. Okay, so we are asked to find moment of resistance here, so we'll go ahead with that. Moment of resistance of the section. Okay, how do I find that? For that, I'll be using the flexural formula itself. M by I is equal to sigma by y. Now what we are interested in this is this m value. So m will come out to be sigma by y into I. Okay, now we have I value which we have determined. Why we can use it, sir? Okay, so this m will be the moment of resistance. Now what about sigma? Sigma is given to us. What is that? It is given in the form of allowable stress. So you need to see that stresses won't exceed these values. What were the values? For tension, sigma was 90 Newton per mm square or 90 MPa, both are same. For compression, the sigma is told as 120. It cannot be more than 120 Newton per mm square. So this has been given. So you need to use these values in this equation now. I we already have it. Why? What is the distance of extreme fiber? Okay. Now you have what we have here is once we have located the position of neutral axis, I'll be getting two values of y max. What are those two values? The top fiber and bottom fiber, extreme fibers in this section, in this T section, they are not at the same distance. In a rectangle section, what we had taken earlier, they were at the same distances, d by 2. Here, that will not happen. Here, if you look at this section, okay, y bar from top end, it is 53.72. Distance of bottom most fiber, it will be not the same as topmost fiber. Okay, so what it comes out, I'll write those two values. This is distance of topmost fiber from neutral axis 53.72. Okay, bottommost fiber, what will be the distance of bottommost fiber now? Here the total depth will be 180 plus 6, 186. So here it is 186 minus 53.72, which is 132.28. This is 132.28 mm here. Okay, so you can see the top and bottommost fiber, they are not at the same distances now in such a section, in T section over here. So you have y max here as y max is 132.28 mm here. Okay, we will consider the extreme most fiber. Extreme most fiber, it may be top or bottom, it may be coming on any of the sides over here. So if I use this and if I find the moment of resistance, okay, considering both the stresses, tension and compression. So this is, wait, just a minute, let me make it as not y max, we'll take this to be bottom and y top is 53.72 mm because both have been asked for, sagging and hogging. First case, under under sagging moment, okay, what happens in this case? Tension is on bottom and compression is on top, sagging moment. Okay, this is the nature of sagging moment. Okay, so this is what the sagging moment is. So under such a situation, tension is on bottom and compression on top. This is what is going to occur. So if you get the values of m from considering these two, what happens? So moment of resistance. Okay, we will calculate moment of resistance by taking the tension in the fibers first. Okay, so here it will be, what is the allowable stress and tension? 90. Okay, divided by, what was the I value for us? 7164.57. So this is 7164.57 into y top. Sorry, y bottom. I have taken the tension, sagging moment. Tension is on the bottom, into 132.28. So what this gives me? See, what I have done here is I have taken the sagging moment first. The first case is when beam is subjected to sagging moment. Okay, when it is subjected to sagging moment, what is happening is bottom fibers are subjected to tension. Okay, top fibers are subjected to compression. Okay, we will have to evaluate the movement by taking the allowable stresses in tension and compression here. Okay, we'll check which one will be the least one. Okay, so in any case, in the beam, the stresses should not exceed these values. In tension, they should not be more than 90 Newton per mm square over here. And in compression, they should not exceed 120 Newton per mm square. Okay. Now, first I have taken the bottom fibers. With respect to bottom fibers, I am finding moment of resistance. So, what is the distance of bottom fiber from the neutral axis? 132.28 mm. So, sigma under tension, bottom fibers are in tension, sigma in tension, allowable stress in tension is 90 Newton per mm square. So sigma by y. Okay, so this is, okay, I've gone, this should be y and this should be I here. So sigma by y, that is 132.28 into 7164. How much was that? 7164.57. 7164.57 into 10 raised to 3. Okay. By considering the permissible stress and tension, we will calculate the moment of resistance first. So what will be this value? 4.87, 4.874 into 10 raised to 6 Newton mm. Is that the answer what you are getting?
Yes,
4.874 into 10 raised to 6 Newton mm, or this is nothing but 4.874 kilonewton meter. Okay, so this is one value of moment of resistance. By what? By considering the permissible stresses in tension. The same what we have to do is we have to determine the moment of resistance by considering the permissible stresses in compression here. Okay, so here for the same beam, okay, what we'll do is we'll have to take the permissible stresses in compression and find out what is the moment of resistance. The same formula is applicable. M is equal to sigma by y into I. But what I'll do is, in this case, I'll take the top fibers, y top. So this will be permissible stress in compression is 120 Newton per mm square divided by 53.72 into 7164.57 7164.57 into 10 raised to 3. Okay, so what this comes out in this case divided by, so it is coming out to be 16.00 into 10 raised to 6. Moment of resistance in this case, it is coming out to be 16.00 into 10 raised to 6 Newton mm. Okay, or I can take it as 16.0 kilo Newton meter. Are you getting these values?
Yes, sir.
Okay. Therefore, under sagging moment, what is the moment of resistance of the beam? This is 16. Earlier it was 4.874. Okay. So least of these two has to be taken as moment of resistance, will be 4.874 Newton mm. Why I'm taking the lower value? This is the maximum moment that the section can withstand. I cannot apply a moment of 16 kilonewton meter to that section because it will fail due to the stresses exceeding in tension. Stresses, when you apply a moment of 16 kilonewton meter under tension, the stresses will go beyond 90 Newton per mm square. So it will fail, it will rupture over there. Okay. So for that purpose, the moment of resistance out of these two, what we are determined on the basis of tension and compression, on the basis of these allowable stresses under tension and compression, the lowest value is 4.874 Newton meter. Okay. Okay, Newton into 10 raised to 6 is there. So it will be 4.874 or 4.874 kilonewton meter. Okay, that is the maximum bending that the beam can withstand under sagging. Okay, you got that? How to determine or calculate the moment of resistance here? Please look into it. In second case, what you have to do? Second case is when the beam is subjected to hogging moment. Please put your US in the chat box. We are running out of time. Second is hogging moment. I'll give this clue for you. You proceed with the solution later. Okay. So when the beam is subjected to hogging moment, compression is on bottom and tension is on the top. Okay. Now what you have to do is, only thing is here y top, when you take this m by I, the flexural formula, and try to find moment of resistance, the sigma value will be changed. Okay, what you have to use is, instead of 120, now this will be 90 when y top is considered, because tension is on top side. When you consider this y top, okay, 90, the value of sigma will be 90. When you take bottom extreme most fiber, the sigma value will be 90, sorry, 120. Okay, so these sigma, what we have used in this first case, they will just change, reverse over there. Okay, so try finding for this case. So here, first m, which you find from sigma is equal to y bottom into I. So this will be on the bottom side, compression is there, 120 by, what was that, 153 point 132.28. So this is 132.28 into 7164.57 into 10 raised to 3. This is one value of moment what you will get. Okay, so bottommost fiber are in compression now. So what you have to equate, substitute for sigma is permissible stress in compression. That is what you have to substitute. Okay, when you take the topmost fiber y top, the top fibers are in tension when beam is subjected to hogging moment. So there you will have to put sigma value as 90. That is the change what you will come across. Okay, do it for the second case. Same procedure is there. Only thing is bottom fibers are in compression. So when you substitute for y bottom, sigma should be 120 Newton per mm square. Okay, when you find moment of resistance by considering the stresses in permissible stresses in tension. Okay, it will be y top, sigma is 90. Okay, so if everybody has given the attendance, I'll finish it over here. Okay, you can exit. Try that one, what I have told for the second case. What is the moment of resistance?